Hello, everyone. So we have Adam Fraser now, and he is going to talk about the Zio. Adam is a core contributor to Zio, a library for asynchronous and concurrent programming in functional Scala. He's also the co-author of Zio test and worked closely with the John Digos in the development of the new encoding for Zio's environment type. So we are excited. Over to you, Adam. You can go now.
Awesome. Thank you so much for the introduction. Let me just share my screen here. So today I'd like to talk to you a little bit about what hopefully Java developers can learn from Zio. So we're going to proceed in three parts here. So first I'm going to tell you about Zio so you have some sense of both what Zio is as well as hopefully why it's something that is interesting and can solve some problems that may be relevant problems that you have faced or are facing or will face. Then I'm going to talk to you about some of the key design considerations behind Zio. And then I'm going to try to take it back and kind of step back from Zio as itself a library that's written in Scala, but how there are lessons from that that I think can be relevant to people who are working in Java, any JVM language, or really any language at all. So to start off, what is Zio? So Zio is a library for asynchronous and concurrent programming written in Scala. And the goal of the library is really to give ordinary developers superpowers for writing asynchronous code. So I think we all know that doing concurrent programming can be really hard. We deal with race conditions, we can have deadlocks, we're trying to have these different things going on at the same time, and sometimes it's kind of hard to reason about what's going on with our code. And so it can feel very difficult sometimes when we want to kind of do something that involves asynchronicity or concurrency that is kind of outside of just, well, there's this specific thing that already does that. And the goal of Zio is to make that very easy so that those of us who are kind of ordinary programmers versus concurrency experts can still take advantage of all this functionality and do really cool things, and in a way think about solving our business problems instead of solving concurrency problems. So to motivate this, I'm going to walk through a couple of examples of things that we might get asked to do. And we'll see both kind of why those seem like hard things to do, as well as how Zio can hopefully convince you that Zio can be kind of magical in actually making these hard problems really easy. So our first problem is we're asked to open a collection of files in parallel, and then we're going to perform some analysis with the contents of each of those files, and we're going to aggregate them all together. But we've got some constraints here. We're never supposed to have more than 4 of these files open at the same time. And as we read these files, we're going to be parsing them, and we might run into some kind of error. And if we do, we want to abort this whole thing immediately. We want to stop reading any more files. We want to interrupt reading the files that we're already reading. And we want to make sure that no matter what, we close all of these file handles. So that actually, like, if we were just asked to kind of do that ourselves, it seems like a kind of hard thing to do. We've got this issue of parallelism here. We've also got this issue of resource handling. So parallelism, we say, okay, maybe we need some kind of semaphore. Resource handling, okay, try finally. We've kind of got that. But then we got this interruption thing that seems like super hard. Like, how do we interrupt? We know, like, we could interrupt a thread, but then we're going to have no guarantee we're going to close these files, and then we're just kind of destroying this thread that's expensive to create. Maybe we can create some kind of atomic Boolean, and we can change its status when we do want to interrupt it, and we have to pass that through everywhere. But like, this seems like we could like say, okay, this is going to be our project for the day of like doing this thing. Here's the same thing implemented with Zio. So we're just going to use this for each par_n operator, which is going to perform some workflow in parallel with a maximum parallelism here. And then we're going to use this bracket operator that's going to open a file. And bracket's going to guarantee that when we're done with using the file, we're always going to close the file no matter what. And then we're going to do our analysis here. So if we get a failure here, this file is going to be closed. And this operator is going to guarantee that all of the other processes are automatically interrupted. And then once we've got the results from parsing all these files, then we're going to analyze them together. So let's look at how that solved each of those problems we talked about. So that for each par_n operator is going to perform that workflow in parallel for each element of a collection. The parallelism is going to be limited there to the maximum level of parallelism we specify. And if any of those workflows fails, all the others are going to be automatically interrupted. Resource handling. We had that bracket operator. It guarantees that if we acquire that resource, if we open that file handle successfully, then no matter what happens with the way we're using it, if that parsing of it fails, succeeds, gets interrupted, that resource is going to be closed no matter what when that is done. And so it's like that try finally we talked about, but it also works in the presence of interruption. And then we got this concept of interruption, which seemed really hard and something we didn't really have support for in a lot of the things we do. And when working with Zio, each of these Zio effects is you can think of as a workflow that describes a series of steps in that workflow. And any workflow can be interrupted between any step in the workflow. And if it is, it can have finalizers associated with it that are guaranteed to be run. And that guarantee applies even if it's interrupted. And then, of course, we have the ability as well to designate certain sections of our code as interruptible or uninterruptible if we have certain critical sections that we say we don't want anything messing with us while we're in the middle of this because we need to finish what we're doing. So that's one example of what seemed like a pretty hard problem that becomes, I mean, if we go back to that code here, it becomes both pretty straightforward and pretty declarative of we've kind of got the tools that let us do each of these things, and we're not having to think about the implementation of it. That's already been thought of for us, and we can use that to solve whatever problem that we're dealing with. So here's another one. So let's say we have an actor system, and we've got two supervisors that are each supervising a set of actors. And we want to have a concept of being able to transfer one of those actors from being supervised by parent one to being supervised by supervisor two. Challenge is that, so we've got two different mutable concurrent sets here, or not even concurrent, we just got two mutable sets here. And we've got to remove from one, we've got to add to the other, and we've got to make sure there are no other updates at the same time that get made to either of these sets of actors that are being supervised. And we also want to make sure we're not blocking any threads in the process of doing this. So what are the issues here? Well, first we've got this issue of just concurrent state, that we've got this state of each of these supervisors that is potentially being modified in different ways by different threads. And then we've got this hard issue of essentially each one of these we could maybe update as on its own, but we need to make sure that removing the actor from being supervised by one and adding it to being supervised by the other occurs atomically, so that no one is ever able to observe a period where this actor is not being supervised by anyone, or being supervised by two people, or we have any other kind of inconsistent state there. And then we also have this issue of blocking of like, okay, like so far you might say like, okay, we kind of need to synchronize on one and synchronize on the other. And that's, that has its risks, and we can kind of deadlock, we have to be careful with that, but we kind of like, okay, we can conceptually do that. But then we say, well, we don't want to block any threads here. Well, now that seems like that's going to be really hard. Like, how are we going to do this? And so one of the things that Zio has is functionality for what's software transactional memory, or STM, and what's called a data structure called a T reentrant lock, which is like a read-write lock, but it's one that can be composed together. So we can imagine each of our supervisors having its own lock. and then we can compose those locks together. So we can say, well, we're going to have an effect here where before we do anything, we're going to acquire the lock from the supervisor we're transferring from, and acquire the lock to the supervisor we're transferring to. And then we're going to commit those together to one transaction that's going to be done atomically. And then we're going to do the same thing for releasing the locks. And then we're again going to use that bracket operator we saw to acquire the locks and guarantee when we're done with it, we're going to release the locks. And then within this, we have a block of code where at this point, we're guaranteed that there's only ever one thread executing this at a time. And so now we can safely and just very simply remove that actor from the one that where it's no longer being supervised by and add it to the other one. And here we'll return a Boolean of whether we were successful in doing this transfer or not. And again, we get a bunch of really nice guarantees from this STM functionality. So we get the ability to compose these updates together, which if we tried to do it just with ordinary locks would be like another like really hard concurrency problem that like we really need to think about and really make sure we were smart about to get right. And this is all done by a model of optimistic concurrency where we're essentially going to do those transactions. And if any of those transactional variables gets modified by another concurrent process, then we're just going to retry that transaction. And it's done in a very efficient way where it's never going to block. Those retries are only going to be done when one of the underlying transactional variables changes. So we're also never going to be doing some kind of like busy loop where we kind of keep doing the same thing and we're spinning and just using system resources while we're waiting for this state to occur. So hopefully those are a couple of examples that have motivated you that this is pretty interesting. This can take problems that were hard problems and make them a lot easier to deal with. So other than just like, okay, Zio is a cool library. If you're using Scala, you should check it out. What are some of the implications of this, and how does Zio actually do this? So I think the first design principle I would say underlying Zio is this idea of separating, describing what we want to do from how we want to do it. So here's a really simple example of a Zio program. And so each of these Zios you can think of as a workflow. And it's a description of some workflow. It's not actually doing that workflow. So here, when we do this effect total operator and we're just printing hello world at the console, nothing's going to happen when we actually do this. What we've done here is essentially created a description of a workflow that when we run it is going to print hello world. But at this point, this is just a description of a workflow. And that has a couple of advantages. The most important is that by separating that, we can then decide how we want to interpret that. And in particular, we can build our own essentially runtime on top of the JVM that takes these descriptions and turns them into actual code that gets executed that does things like printing things and accessing files and opening network connections. And that gives us a lot of power. So here's an example of a little bit of what this looks like. So this Zio workflow we've been talking about, you can think about it as forming also a miniature language that exists within this host language of Scala. And it's got its own terms. So like when we call effect total there, all we're really doing is we're just returning this new just data type, right? All this is essentially an enum that just contains this func that eventually is going to execute this body of code that we put into it. And there are less than 20 of these primitive elements in this Zio language, but we can put them together to do all of these things, partly because we can just embed code that we want to from Java or from Scala into this Zio mini language. And then once we've described these things, we then have the ability to go out and actually translate those back into something that runs it. And so we've got a couple of methods that do that. They generally have this like unsafe signature in front of them because we want to indicate these are the only things that don't describe things, but that actually turn those workflows into running those workflows. And so this is going to take that workflow that describes a value that's going to produce an A or potentially fail with an error E, and will actually give us the A, or otherwise it'll throw the error. And so that lets us provide features that aren't supported by the host language. So like before, we talked about interruption, and there's still not great just at like the JVM level support for interruption, because there are all these issues with if you interrupt a thread, you don't kind of get guarantee of what state you're in after you do that. And there's been a lot of like good progress with Project Bloom and all these things, but at least so far it seems like that's something that's still kind of on the drawing board versus that we're definitely going to have by this date. And it also allows a faster release cycle, because this runtime you're supporting, if you make changes to that, you're only making changes to the people who are using your Zio software, whatever software you write. Part of the problem with making a change to the actual Java is there are all these people using it, all these different versions with all this different legacy code. And so you can't change things unless you really, really work hard to make sure that your change works with all the stuff that was out there before. So first principle I think about is that idea of describing, not doing, and the power that gives us. Second one, related to that, and we were leading into that a little bit, is this idea of fiber-based concurrency. So one of the fundamental operators in Zio is this one called fork, which normally you would think of, okay, fork is I'm creating a new thread and fine. But in Zio, it creates this thing called a fiber versus a thread. And a fiber you can think of as a green thread, as a user land abstraction over a thread. But essentially, a fiber just describes some process that's running potentially concurrently with other processes that is not necessarily an operating system thread. So when we have these fibers, Zio has its own runtime that's going to submit the workflow that fiber is describing to a thread pool, but then that thread pool is only going to execute it for a specified amount of time, either until that workflow explicitly yields back or until that workflow executes a given number of steps. And so that both allows Zio to support concurrency on platforms like JavaScript that don't actually support having multiple threads that are going on at the same time. But it also allows providing functionality like interruption there, because now if the Zio runtime is managing this, interruption isn't interrupting a thread. It's just essentially, as the Zio runtime executes each step, it's going to check for interruption. And if the process has been interrupted, then it's just going to stop executing that workflow. And then it's going to go to see what finalizers are associated with that. And it's going to start executing those finalizers. And so it's an example of that power that when you describe, then you can create your own interpreter and you can build a lot of functionality into that. And it also allows awaiting an interruption and without blocking. So we'll see that on the next slide here, where here's a simple example of some code written with Zio. And so all we're doing here is we're making a promise, and this is not a Java promise or a Scala promise, this is a Zio promise. And then we're creating this concurrent process here that is going to complete the promise. We're going to delay 5 seconds before we do that, and we're going to fork this whole thing into a new fiber. And then on our main fiber, we're just going to await the promise completing. And so the cool thing about this is that this code is never going to block any operating system threads. So both the delaying 5 seconds here and awaiting the promise are internally implemented as callbacks. So when we say delay here, we just tell the runtime, okay, stop executing this, go ahead, execute other things. And after 5 seconds has passed, start executing this again. But no thread is actually ever waiting to do work here. And a similar thing happens when we await the promise. But with this, and this syntax is called a for comprehension Scala, and it just kind of lets us write one step after another. With this kind of syntax here, this looks very imperative and sequential, right? You can read this as do this, then do this other thing. And so it's a really nice example of how this type of interface lets you write and reason about your code in a way that feels very linear, where you're not kind of having callback, nested and callback, nested and callback, but you still get all the efficiency of not actually ever blocking here. And some of this you're going to get over time with Project Loom and virtual threads, but some of this, when we talk about things like interruption, you're not going to get. And if you do this, you're all set in the same API, essentially, both today and several years from now. Third design principle I would think about from Zio is compositional laws. So to build larger components out of smaller ones, we need laws that tell us how those components behave. And those laws need to fit together in the right way so that if the components follow the laws and we put them together in the right way, then the overall system we build will follow the laws. And those ideas are definitely not unique to Zio, but there's something that I think we spent a lot of time thinking about, and particularly that idea of how do they fit together. So if you go back, for example, to that first problem we looked at with opening the files and then making sure they were closed, we used this bracket operator. And when I was telling you about it, one of the things I said was that it has this guarantee that if the acquire action completes execution, if we open the file handle, then no matter what happens with how we use the file handle, that file handle is going to ultimately get closed. And that was a powerful guarantee that let us reason about how the overall solution we were building was going to solve our problem. And in addition to that being powerful, it was important because it fit together in the right way with the other things we were doing. So that guarantee, it holds regardless of where we call this bracket. So whether we called it in a concurrent process, like when we did that for each par n, or whether we call it itself, wherever we call it, that guarantee is going to apply. And it's also going to apply regardless of what's in these effects. These could be opening and closing files. They could be opening and closing network connections. They could be logging some information that the process has done. We don't need to know exactly what's happening in each of these. The guarantee still applies. And so when we take things like that, and then we take that and we put it together with that guarantee we got from that for each par n operator that says, hey, I'm going to do these things in parallel, and if any one of them fails, I guarantee you I'm going to try to interrupt all the other ones. So then you say, okay, well now I can build these more complex systems on top of that. So that's a little bit about Zio, and I think hopefully already you're kind of seeing some of the ideas here of this is not just Zio or just Scala, but there are things that are relevant more broadly. But in the final section here, I'm going to try to draw out some of those, at least from my perspective, of what might be some of the takeaways that apply more broadly. So the first one is, I don't think there's anything here that is truly Scala specific. Zio's written in Scala. Scala is a fantastic language. I think it provides a lot of functionality that has helped us provide a very nice and ergonomic user interface to take advantage of this. But the reality is there's nothing here in kind of the underlying what we're doing that couldn't be done on Java, in other languages. In fact, there have been ports of Zio to TypeScript. So it's definitely not Scala specific or even JVM specific. The second thing, and I think maybe this is the most important, is this idea of the need for higher level operators. So at least and admittedly, I'm kind of in Scala and in Zio, but from my vantage point, it seems like there's a lot of operators that are pretty low level. If you think about like what's in the Java util concurrent package, or even some of the things that are kind of built as like a little bit more advanced abstractions on top of that, of like a Guava or something like that. And in a way, they're like fantastic. There's a ton of amazing thought that went into putting those together, making them very efficient. You can use them to do a lot of things. And in fact, Zio internally uses a ton of these things to actually implement the functionality it provides. But I think maybe what we miss a little bit is actually like how low level they are, where when we want to do problems that are actually relevant to us, like we have to drop down to this pretty low level, right? And so we're kind of stuck between like, if we want to do something that like fits into like what an existing framework provides of like, okay, Kafka lets us do this, or Cassandra lets us do this, then we're like, okay, great, we do those things. But when we kind of need to implement our own stuff, then we kind of go back to this like very low level stuff. And then we've got to like end up rebuilding a decent amount. Versus I think there's a little bit of like a sweet spot of what Zio provides, where we get like that for each par n operator. That's something that is like pretty intuitive and probably pretty useful across a lot of things, of saying, I want to do a bunch of things at the same time and take the results and pull them all together when they're done, is a pretty common thing. And it has this nice behavior of making sure that if one fails, then there's no point in doing the others because we already have a failure. And things like that make it a lot easier for us to focus on solving our problems versus solving these concurrency problems that are really probably not specific to our domain, but that are more general. Then there's this idea of separating the describing from the doing. We talked about that before. I think it's a really powerful technique in general because it gives the ability for us to write a way to interpret that program that actually can see and optimize more of it, because we're not doing each step at the same time. We're putting together a description, and then we're able to look at the whole description we create and say, okay, how do we want to run this thing? And again, we can use that to support features we want that maybe don't exist if we just do it one step at a time in whatever language we're working in. And then finally, this idea of defining laws that compose, that we want to be able to build a more complex system by putting these Legos together. And for that to work, the whole system has to have properties that emerge from the properties of the simpler ones. And so we need to think about how both we say, okay, this component of our system gives these guarantees, but also how those guarantees fit together so that if we're building something much bigger, we can understand how it works without having to go into like this little aspect of it, but we can just say, okay, we put it together this way, it's going to have these properties. So with that, I think I'm just about out of time here. So to sum up, Zio is a library in Scala, gives you superpowers for writing asynchronous code, written in Scala, but the ideas are, I think, definitely not limited to Scala. And in particular, I think this idea of implementing higher level abstractions is one that can apply to Java and other languages. And there's definitely a trade-off there of like, Zio's got some overhead associated with it, of if you want to do something that's very low level, you probably are going to be more efficient doing something with one of these lower level tools like Java util concurrent. But I think the reality is a lot of times we're doing things like network IO, where the time for whatever we're doing is dwarfing the time that any of these tools are operating. So there's also value in our time as developers, and we can save a lot of time by using tools like this. With that, I'd like to thank, John DeGoes is the original developer of Zio. It's been an incredible leader of the community around that. So if you're ever interested, check it out. We'd love to have you contribute, ask questions, learn. Everyone else who contributed to Zio, everyone who's used Zio and given us feedback, which has been tremendously helpful. And then Ollie and all the team here for organizing this incredible conference and giving me the opportunity to talk to you today. And finally, all of you for attending.